Hello, I am Tyler Marcus, and I created the GUI for our project, and I will be demonstrating how it works in this video. So I added four UI axes in order to demonstrate different parts. So this was, for example, if I just load the regular dog image PNG, it shows up in the normal image. This is the normal image that you select to load. If you, through this image, which is the image to hide, is where the images that you select to embed into the normal image, that's where they show up. They show up in the image to hide axis. And then when you click, for example, any embedding technique, and then click embed, you get back this image with the regular image with the image embed. And obviously you can just click recover here and recover and get the secret image. However, you can also let's just reload the dog image.png, and then select a different one, embed it, and then you can save the image, and let's call it embedded 7.png. You can save it, and then you can load embedded 7, and then recover this same image with the same technique by uploading images from your files that already had that had previously been embedded. And just to demonstrate, for example, I can load image 1, and then load dog image.png, and then this is with a different embedding technique. Can embed and recover this image, and then 3, let's embed this, load dog image.png, embed this, and then recover it, to demonstrate multiple techniques work to embed and recover the image afterwards. So it's just getting all the embedding techniques to work properly with the callbacks, and also with the list select image box to get this value right here, so that way that what you select in the list shows up in that one UI axis to show you what image you're going to be embedding. Yeah, and that's about it. I use switches in order to switch between different embedding techniques depending on what technique you were using. So depending on the case, odd, even, red, odd, even, blue, whichever one you select in the drop-down menu. And yeah, and yeah, that's probably about it for my contribution to the project.
My name's Orion, and this is the first function that I worked on. This is a flatten image function. It's pretty simple. It takes a grayscale image. Essentially, if it is lighter than the value 128 out of 255, then it'll turn that into the value 1, which is white, and it'll turn anything else into the value 0, which is black. So it makes a black and white image. And then our expanded image function, it turns a grayscale image into a RGB image by expanding it with the repmat and uint8 functions. So this is a big function that I worked on. It's called all odd even embedding. For this function, we first created it I created the red odd even embedding function, and Ronin created the green and blue all odd even embedding functions, and we decided it would be a lot easier if we just put this all into one function and used an RGB value in order to iterate through, whether it's red, green, or blue. So what this does is it takes our hidden, it just reads our hidden image and our user inputted image, and it flattens the hidden image into black and white. And then with that being binary, first we check all of the white images. And if the image is white, then we use a mod function to check if the value on the original picture is odd or even, and if it's not even, it makes it even. Otherwise, if the pixel is black on the hidden image, then it'll turn the corresponding pixel on the original image into an odd value. That way, for example, when we call this function, can't really tell a difference, but if we were to change one of these values, we make it even more clear by just like inputting 100. Boom, there we go, very clear. You can see our hidden image in the lines here. And then that works for if we use 1, it works if we input 2, and it works if we input 3.
My part of the project, I implemented several of the core steganography algorithms used in the embed and recover hidden images. Looking at this piece of code right here, the embed mod3red function is responsible for embedding a hidden image into the red channel of the host image using a modulus-based encoding method. First, the hidden image is loaded using the MATLAB imRead function, then the host image, which in this project is a dog image, is loaded as well. Next, the hidden image is passed into the flattened image function, which converts the grayscale image into a binary matrix consisting of zeros and ones. The binary representation makes it easier to encode the hidden information into the pixel values of the host image. Next, the program iterates through every pixel of the image using nested for loops. This line extracts the red channel value of the current pixel. In MATLAB, images are stored as three-dimensional matrices where the third index represents the color channel. Index 1 corresponds to red, index 2 corresponds to green, and index 3 corresponds to blue. This section performs the actual embedding. The value of the hidden pixel determines how the red channel pixel should be modified. If the hidden pixel is 1, representing a black pixel, the red channel value is adjusted until the remainder divided by 3 equals 1. If the hidden pixel is 0, the pixel value is adjusted until the remainder equals 0. The MATLAB mod function calculates the remainder, which allows us to encode binary information inside of the pixel value without making noticeable changes to the image. Finally, the modified value is written back into the red channel of the image. The min function ensures that the pixel value never exceeds 255, which is the maximum value allowed in an 8-bit image. The recovery functions reverse the embedding process. In this function, the first step is extracting the red channel from the image using the MATLAB matrix indexing. Next, the program checks the modulus of each pixel value in the red channel. If the remainder when divided by 3 equals 1, then the recovered pixel is set to 1, representing a black pixel in the hidden image. Finally, the expand image function converts the binary matrix back into a visible image by transferring zeros and ones into black and white pixels. The program then checks the parity of each pixel value using the mod function. If the value is odd, the result is 1, and if the value is even, then the result is 0. This reconstructs the binary hidden image. Finally, the binary matrix is expanded into a displayable image using the expand image function. The recover odd even green and the recover odd even red operate similarly to the blue recovery function, but it extracts the green and the red channels instead. Overall, these embedding and recovery algorithms allow multiple hidden images to be stored inside a single host image by modifying pixel values in a different RGB channels. Because the changes are very small, the hidden data can be stored without noticeably affecting the appearance of the original image. One important aspect of this project is that the pixel values are only modified by a very small amount, usually by plus or minus 1. Because RGB values range from 0 to 255, these tiny changes are generally not visible to the human eye, which allows for hidden information to be stored without noticeably changing the appearance of the image. Another advantage of using RGB images is that each pixel contains the 3 separate color channels, red, green, and blue. This allows us to embed different hidden images in different channels without them interfering with each other. For example, one hidden image can be stored in the red channel while another is stored in the blue channel.